To understand the order of doping in emitter, base and collector region in a BJT, let's take an example of NPN transistor. So we are taking an example of NPN transistor. So in NPN transistor, we have three regions. One is emitter, another is base, and third one is collector. So these three regions are emitter, base and collector, and we are taking example of NPN transistor. So this is NPN transistor. So in emitter, majority carriers are electrons, and in base majority carrier are holes, and in collector majority carriers are electrons. So we want these majority charge carriers to get collected in the collector region. So for that, what we do is we make this emitter base junction forward bias. So this is how we will be applying a biasing voltage, let us call it VBE. So what will happen, there is a width of depletion region which will be less for this junction. This is called emitter junction and this is called collector junction. So width of depletion region will be less for emitter junction because we are applying forward bias. So in case of forward bias, potential barrier will be lower and electrons from emitter to base and hole from base to emitter can easily go comparatively because we are applying forward bias now. So these electrons will be going in base region, and in base region these electrons are minority carrier, so they will be recombining, and similarly the holes which are majority carrier in base region will be going into the emitter region and will be recombining. Now the electron which are going from emitter to base are minority carrier in base region, and we want most of those minority carriers to get collected in this collector region without recombining in base region. So for that, what we do is we make this base width. So we make this base width small. So we make width of base small. Now we cannot make this base width very small, because if we make base width very small, then what will happen? The area will be reducing, and we know rho equals to RA by L, and R resistance is going to be rho L by A. So if this area is reducing, then resistance will be increasing. So the series resistance in this base region will be increasing, and the voltage we are applying will drop across this R, and some of the voltage is not dropping where it should be, but it is dropping across this R, which is not useful controlling the device. So we lose some of the control of the device, that is another problem. So what we do is, so one way to get rid of this is we focus on this resistivity and we reduce this resistivity. Okay, how do we reduce it? If resistivity is reduced, it means that we are increasing the conductivity, and for n type the conductivity is NQ mu n, where Q is charge of the electron and mu n is variable which is not appropriate to vary it, and we can vary n. So n is number of electrons. So how we will vary number of electrons? N depends on doping. So if we increase doping, then number of electrons will also get increased. If number of electrons are increasing, then conductivity is also increased. So it means that we have to dope. So doping of emitter has to be high. So doping of emitter has to be higher. Now when we are making this junction forward bias, electrons are going from emitter to base and holes are going from base to emitter. So electrons are going from emitter to base, and we want those electrons which are minority carrier in base to get collected in the collector. So that is good thing that electrons are going from emitter to base. But what about the holes which are going from base to emitter? Is that good thing or bad thing? Let us see. So for this we have a parameter called emitter injection efficiency, that's called gamma star, and that is INE divided by INE plus IPE, where INE is part of the emitter current. With this INE is part of the emitter current carried by the electrons. So whatever electrons are going from emitter to base, due to those electrons the part of emitter current is carried by INE. Now IP is part of the emitter current which is carried by the holes which are going from base to emitter. So this IPE is not useful because the holes which are going from base to emitter are just recombining, they are not contributing in the collector current. But INE is useful because that is the only one we are absorbing in collector. So this INE has to be much greater than this IPE. So IPE, right? So we want this IPE is negligible with when compared to INE. So ideally we want this emitter injection efficiency almost equals to 1. So when it will happen? When this INE is much greater than IPE. Now how we can reduce IPE? How we can make negligible IPE when compared to INE? So we can make IPE negligible when we restrict the holes which are going from base to emitter. Okay, if less number of holes are going from base to emitter, then IPE will be less. Now how to do that? So one way to do that is we make doping of emitter higher as compared to doping of base. If doping of emitter is higher, then more electron will come in base. If doping of base is lower, then we have less number of hole, then less number of hole will go from base to emitter. So this is one of the way. Now another way can be, in base we introduce different type of semiconductor which are having lower band gap. Now what will happen? So if we have energy band like this, and if we this is a conduction band, this is conduction band. So electron are going from here to here and holes will be going from here to here. So if we introduce here a semiconductor which are having lower band gap, then the band gap will be like this. It means that the hole which are going from here to here will have higher potential barrier and will have difficulty to go into a base to emitter. So this is one of the way we can restrict the movement of holes from base to emitter, and we can make IPE negligible as compared to INE. So this is another way, but the first method was we can make doping of emitter higher than doping of base. So this is the order of doping of emitter and doping of base. Now let us talk about doping of collector. So to talk about that, so the electron which are coming from emitter to base, those electrons are minority carrier in base region, and we want those electrons to get collected in this collector, right? So for that, what kind of electric field will facilitate this process? That is, electron which are coming in base from emitter should get collected in collector. It means we want the electrons to move from left to right. Then the electric field which will facilitate this process has to be right to left. So the electric field direction has to be right to left. So when the electric field will be right to left in this region, when we will make it reverse bias, okay, so making this junction reverse bias, then what will happen? We will have width of depletion region here, okay. So we will have width of depletion region which will be larger as compared to this emitter junction, because we are making emitter junction forward bias. Now when we are, this is VCB, okay, so this VCB we are increasing to make a higher electric field to get more number of electrons from base to collector. Now when we are increasing VCB, then width of depletion region will be increasing. Now width of depletion region will be increasing, and width of base region will be reducing, right? But we cannot make width of base very less. So for that, what we do is we want effect of this VCB, means when we increase this VCB, we want effect of this VCB less in base region, so that this base width will not reduce much. It means that effect of VCB will be more in collector region and less in base region. Then how can we achieve that? We can achieve that by making doping of base region higher than doping of collector region. So we know if doping of a region is higher, then width of depletion region in that region will be less, and if doping is lower, then width of depletion region in that region will be higher. So with this, width of depletion region in base region will be less, and we can avoid getting base width too small. So this is how order of doping of base of collector is, and we have seen that doping of emitter was greater than doping of base, and here we saw that doping of base is greater than doping of collector. So this is the order of doping of emitter, base and collector. Now the question may arise is, sir, you are making doping of collector small as compared to doping of base. When VCB is increasing, then what will happen? Width of depletion region will be more in collector as compared to base. It means that you are increasing the resistivity of this collector. It means you are making less conductive this collector region, and collector is output terminal. And how it can be possible that output terminal is more resistive? How is it possible this output terminal is less conductive? Well, that's a valid question. Then answer of this question is, let us say we have emitter, base and collector. So this is emitter, this is base and this is collector. Now to answer this question, what we generally do is, in collector region, this is collector junction, this is emitter junction. So in collector region, nearby this collector junction, we make doping N minus. So this is highly doped N plus, this is P, this is we are making N minus nearby this collector junction, because up to this time only action of transistor or job of this transistor is done. After that, this is just a connection. So we make it N plus. So we make it N plus, and the output terminal will not be less conductive. So this is conductive. So this is how we can say that emitter doping is greater than base doping is greater than collector doping. So this is the logic behind this order of doping of emitter, base and collector, and I have already made a video where I provided 10 authentic proof in the standard books where this order is taken. So you can check out that video in top right corner. So this is all about this video. Let's end it here. See you in the next one. Thank you.